Hi everyone, welcome to this week's live stream. So today we are going to be working some stoichiometry problems. We're going to start with stoichiometry that has gas laws in it, and then we're going to do some problems that have limiting reactants or limiting reagents. So let's go ahead and get started with our problems. All right, here we go. First problem, let's just read it. Ammonium nitrate decomposes when heated. The reaction is shown below. If 45 grams of ammonium nitrate fully decompose at STP, how many liters of water vapor are formed? Now, there are, of course, always a couple of things that I like to focus in on in the problem. First, it's a stoichiometry problem. We are given information about ammonium nitrate, which is right here, and we are asked about liters of water. So we need to connect this with a balanced chemical equation, which of course we were given. Always double check, make sure it is balanced properly. So let's just check. Yes, nitrogens, hydrogens, oxygens. Say again? Okay, thank you. Okay, so let me just turn my mic down a little bit, and hopefully that is better. Okay, back to the problem. So whenever we're doing stoichiometry, we know we're going to use a mole ratio. So the first thing that we need to do is we need to convert these 45 grams into moles. And the way we do that, of course, is with the molar mass. So let me just switch up to my pen. And we're going to have 45 grams. That's an H of ammonium nitrate. And let's convert that into moles. Now I do already have the molar mass of ammonium nitrate, and that is 80.043. Okay, so let me see if I can fix my audio here. Hopefully this is a little bit better. I've got to find that sweet spot where you guys can hear me, but I'm not blasting. Okay, so this is the molar mass. Sorry, got a little distracted there. Ammonium nitrate, and that of course is over 1 mole of ammonium nitrate. Okay, so we have now our grams of ammonium nitrate are going to cancel. That is fantastic. What we need to do is the problem asked us about water, so we need to convert to water using our mole ratio. So our ratio is 1 mole of ammonium nitrate to 2 moles, that is an M, of water. Again, these numbers come from the stoichiometric coefficients right in front of our chemical equation. Okay, now we need to talk about our gas laws, and specifically we're going to talk about STP. STP stands for standard temperature and pressure. And standard temperature and pressure is 0 degrees Celsius or 273 Kelvin and 1 bar. Now, the key thing here at STP, I'll go ahead and write this down in the corner. At STP, an ideal gas, which we are assuming here, has 22.4 liters per 1 mole. Now this is only at STP. You can only use this conversion factor at STP. The temptation is later on in other problems where you're not at STP, it's very tempting to use this 22.4 liters per mole. However, in this case, because the problem did specifically specify STP, we can use this 22.4 liters per mole. So let's set up one more conversion factor. And that is going to be in 1 mole of our ideal gas, in this case water vapor, there are 22.4 liters. That is an O there. So now we can see that our moles of ammonium nitrate canceled and our moles of water canceled. We are left with this, I did not specify, this should be liters of water, and specifically water vapor, because we've got the gas here. And now we just need to do our calculation. So I have done that calculation, and we get 25.2 liters of water vapor. So the nice thing is when you're at STP is you can put all your conversion factors in a line. Again, I call this smashing, but we will see in the next problem that we cannot always use this. All right, so let's first read our problem as we normally do. Aluminum reacts with hydrochloric acid to form hydrogen gas as shown below. How many grams of aluminum are needed to form 850 torr of hydrogen gas at 85 degrees Celsius in a reaction chamber that is 90 liters. Clearly, we are not at STP. However, we are still going to assume ideal gas behavior. But let's first identify this as a stoichiometry problem. So we are asked about aluminum, but we are given information about hydrogen gas. So again, to connect those, we need a balanced chemical equation, which thankfully we already have. So we are now mentally prepared to do stoichiometry, and I'm already thinking, okay, to do stoichiometry, I'm going to use my mole to mole ratio, which means I need moles. I have no moles anywhere here. Now, because we're not at STP, I cannot use this 90 liters and the conversion factor 22.4 liters per mole to convert to moles, because we are definitely not at the correct pressure or the correct temperature. So I need another way to convert all this information about hydrogen gas into moles. And the way we do that is with our ideal gas law. So let's go ahead and write that down. Okay, so of course, let's just get our ideal gas law equation written down. So this is PV equals nRT. P is pressure, V is volume, N is number of moles, R is your universal gas constant, and T is temperature. The one thing I do want to mention for temperature, make sure you convert to Kelvin. Do not put your temperature in this formula still in Celsius. So that is something that we will do on the fly. Okay, so let's plug in everything we know for our ideal gas law. We have 850, that should be a 0, torr. We have our volume here. That is 90 liters. We are trying to find N, or the number of moles, so I'm just going to leave that as N. Now we need to choose an appropriate value for R. There are lots and lots of values for R. I want to choose something that already has the units that I'm using so I don't have to convert too much. So because my pressure is in torr and my volume is in liters, I am going to use the R associated with liter torr or torr liter. And that constant is 62.3 0.364. And the units there are liters, torr over mole K. So if you're ever unsure if your R matches, just check all of your units. We have torr here and torr here, liters here, liters here. Of course, N is going to be in moles. And the last thing we need to do is we need to put our temperature in Kelvin. Of course, they gave it to us in Celsius, so we will need to convert that into Kelvin. And that is just 358 Kelvin. Okay, so I will actually show how all of these units cancel. So our liters cancel, our torr cancels, our Kelvin cancels. We are left with mole, which is the value for N. So when we do this calculation, we will get out moles, and in this case specifically, this is going to be moles of hydrogen gas, because these are all the conditions of that hydrogen gas. So let's do that calculation. And we get N is equal to 3.43. That 3 didn't turn out so great. There we go. Moles of hydrogen gas. Okay, great. We have moles, which means we can go ahead and do our stoichiometry and use our mole ratio. So I am going to start a new calculation, starting with my moles of hydrogen. And now I want to convert into, let's see, go back to the problem. We're going to want grams eventually, but we want aluminum, so we need to convert to aluminum. So I'm going to have 3 moles of hydrogen in the denominator because I want my moles of hydrogen to cancel. Again, this 3 is coming from my balanced chemical equation. I'm going to aluminum, so that is going to be 2 moles of aluminum. And now you can see that my moles of hydrogen have canceled. Right now I have moles of aluminum, but the problem did ask me for grams of aluminum, so I have one more conversion factor to put in, and that is just a simple conversion from moles to gram using the molar mass. So in 1 mole of aluminum, there are 26.981 grams of aluminum. Let's make sure my units canceled. My moles of aluminum cancel. I now have grams of aluminum, although that G did not turn out so great. There we go, that's a little bit better. So now, doing the calculation, we get 61.6 grams of aluminum. Okay, let's see if there are any questions. No questions. All right, so you can see how even though we've thrown in gas laws, we're still doing our stoichiometry the same way. We're still looking for moles, we're looking for a mole ratio. We just have a different way to get to moles. Back when we did gram to gram, all you needed was the molar mass to convert. But I do want you to see that there is a pattern here. And sometimes you change the pieces, but generally, overall, there is a pattern. Okay, so that is our gas laws, or our ideal gas law. Let's go to the next problem. I think we've got one more here. Okay, let's read it. When ammonia is burned in pure oxygen, nitrogen monoxide and water vapor are formed. If 18.5 liters of ammonia are burned at 450 degrees Celsius and at 0.75 atmosphere, what is the final pressure in torr of the water vapor formed? And let's see, we're given that the final temperature of the products is 465 degrees Celsius and the final volume of the water vapor is 13.2 liters. Wow, we've got a lot of information here. But let's start by identifying it as stoichiometry. Okay, so we are asked for the final pressure of the water vapor, okay? And we are given a lot of information about ammonia. So this is a stoichiometry problem. We've got to link these two compounds with a balanced chemical equation, which thankfully we are given right here. Now again, I'm thinking stoichiometry. I'm thinking moles. How do I get to moles? I have no moles here. I don't have grams. I'm not at STP. Well, we do have ideal gases, so we are going to use the ideal gas law again. And just looking at how much information we have, and we've got lots of information, I am preparing myself mentally to use ideal gas law twice. But let's go ahead and start with ammonia. And I'll tell you this, the reason why I start with ammonia is because I have enough information to get moles. So sometimes if you're unsure where to start, just look at the information you're given. I don't have enough information to get number of moles of water vapor. Also, of course, the question is asking me information about water vapor. That's another clue that maybe hold off on the water vapor and start with whatever else you're given. There are usually two or a couple different ways to think about these problems. Okay, but let's get to calculating. So let's go ahead and write down our ideal gas law. And let's fill in what we know. Okay, so we have 0.75. That is not writing very well, is it? And that is atmospheres. Okay, that is our pressure. Our volume is 18.5 liters. We do not know moles. We want to know moles. I'm going to need a value for R. I don't like to convert everything into something specific and use a specific value for R. I always like to make my R fit what units I am using. So because I'm using atmosphere, liters, and of course temperature will be in Kelvin, I'm going to use the appropriate R, which is probably the one that most people use most often. You might be the most familiar with. Okay, so this is liter atmosphere over mole K. And my temperature is 450 degrees Celsius. Again, make sure you convert that into Kelvin, and that is 723 Kelvin. Okay, let's double check. I want to make sure that all of my units are lining up and they're going to cancel like I expect, because that also gives me confidence that I have used the correct value for R. So my atmospheres cancel, my liters cancel, and my Kelvin cancel. I'm left with mole, which is what the value of N is going to be in. Okay, so let's actually do this calculation. So if you put that in your calculator, you will get, that should be a 0, 2, 3, oh, that did not work. Try again. 0.234 moles of ammonia. Okay, that's great. We've got our moles of ammonia. We're maybe a little bit closer to answering our problem, but we're not there yet. So let's go back. Ammonia is taken care of, but again, we're trying to get to water vapor, so now I am going to use my mole ratio to convert from my moles of ammonia to my moles of water. I'm going to start a new calculation. I'm going to start with my moles of ammonia. And I'm going, that should be a 3. I'm going to convert to moles of water vapor. So using my stoichiometric coefficients here, and the denominator is my 4 moles of ammonia, and my numerator is 6 moles of water. And because my water, they give me information, they want pressure, they give me temperature, and they give me volume. I am not going to convert to grams because, again, I'm pretty sure we're going to need to use ideal gas law, and we're going to want to know our amount of water in moles. So I am just going to do this calculation, and I am not going to convert to grams. Although if you ever find yourself converting to grams and you realize you shouldn't have done that, it's easy. Just convert back to moles. It's not a problem. And this gives me 0.351. That did not turn out so well. Moles of water vapor. Okay, just like we thought, back to ideal gas law. Pressure volume equals moles R temperature. So let's plug in what we know. Well, I see right off the bat, I don't know pressure, so I'm just going to leave that as P. That also makes sense because it is asking me what the final pressure is. So it's actually good that I don't know that yet. This means that hopefully I'm doing this problem correctly. Okay, my final volume is 13.2. And that is in liters. I know my volume of, I know my number of moles. I just calculated that. That is a kind of a wonky 3, but that is a 0.351 moles of water. Now for my R, again, I want to choose what's appropriate here. I have volume in liters. Of course, if I got mole, I'm going to change temperature into Kelvin. But the problem did ask for the final pressure in torr. So I am going to use an R that is going to give me a pressure in torr. And that is going to be, again, the 62.364. And that is liter torr over mole K. And finally, again, don't forget, you must convert that Celsius into Kelvin. That is a very, very common mistake that I see students make. So here we are in Kelvin. And before we run through this calculation, I just want to make sure that all of my units cancel and I am getting the unit that I expect to get. So liters are out, mole is out, Kelvin is out. And this is going to give me my answer, my pressure in torr, which is exactly what the problem asked me for. So to do this calculation, my pressure ends up being 1.22 times 10 to the third torr. Okay, so again, hopefully you can see we are still using the basic formula for stoichiometry. We're identifying it as stoichiometry. We are using our mole ratio. But in this case, we had a gas that was a reactant and a gas that was a product. So we had to use ideal gas law twice instead of just once. Now, it would have been nice if maybe one of these had been at STP, but you know, you have to work with what you've got. So before I go on, let me just make sure that there aren't any questions. Okay, all right, great. I love the ideal gas law too. It's very handy. Let's go on to the next problem. Okay, so we are switching gears here. Obviously, we don't have any more pressures or temperatures or anything like that. We've just got moles. But let's just read through this problem first. If 2.2 moles of sodium react with 0.5 moles of chlorine, how many moles of sodium chloride are formed? So first we will identify this as stoichiometry. I have been given information about sodium and chlorine and asked about sodium chloride. And I'm sure you've already noticed I've been given information about both of my reactants and asked about my product. So this is not what I would call a simple stoichiometry problem where we're just going from reactants to products or products to reactants. this is a limiting reactant or a limiting reagent problem. So we need to decide, is the sodium going to run out first or is the chlorine going to run out first? And we need to decide that before we do our actual stoichiometry. Now, the nice thing about this problem is it's very simple and everything is in moles. So we're not even having to mess with converting from grams to mole, or like we just saw, using ideal gas law. We are only going to work with moles and we're going to stay in moles, which is going to make things a little bit simpler. All right, so I need to figure out again, is my sodium going to run out first or is my chlorine going to run out first? Now, the way that I handle this is I am going to run a couple of tests. So this is what I call my test phase. And what I'm going to do is I'm going to say, all right, let's assume that I'm going to use all of my 2.2 moles of sodium. How many moles of chlorine would that take to use every bit of my sodium? And I'm just going to use my mole ratio between sodium and chlorine to figure that out. So my 2 moles of sodium go in the denominator. Again, this comes from my stoichiometric coefficient. I want to figure out moles of chlorine. Of course, this calculation is pretty easy. That would be 1.1 moles of chlorine. So what this test tells me, it says if I'm going to use all of my 2.2 moles of sodium, I'm going to need to have at least 1.1 moles of chlorine. That is how much chlorine is needed to use up all of my sodium. Now again, this is a test, this is a theoretical calculation. But now that I know I need 1.1 moles of chlorine, I need to go back to the problem and say, how much chlorine do I actually have? I know I need 1.1 moles, but how much do I actually have? Well, I only have 0.5 moles. I don't have enough. I am going to run out before it is out. So that means that chlorine, let's put this in a different color, chlorine is our limiting reagent. It is going to limit how much product we can form. Now, there are two things I like to do with limiting reagent problems, because you're going to have a lot of calculations kind of all over the place, a lot of moles all over the place, is I like to make sure that I circle it in my balanced chemical equation. And then, like I've already done here, I like to label it in my calculation. Okay, this is all well and good, but you say, well, how do I know that I need to start with my 2.2 moles of sodium? You don't. You can actually test both of your reactants. I like to test both of my reactants if I have time, because it should confirm that I have chosen the correct limiting reagent. Okay, so instead of starting with my moles of sodium, I'm going to start with my 0.5 moles of chlorine. Again, this is my test. If I'm going to use all of my chlorine, how much sodium would I need? I just use the mole ratio for this. So in this case, I want my moles of chlorine to cancel. I'm trying to predict moles of sodium. That is an N. And of course, this time I am multiplying by 2. So this is 1.0 moles of sodium. Again, this is what is needed. So if I'm going to use all of my chlorine, my 0.5 moles of chlorine, I need at least 1 mole of sodium. How much do I actually have? I need to go back to the problem for that. Well, I have 2.2 moles. I have extra. I have excess. That means that sodium is in excess, which again means that chlorine is my limiting reagent. So you can see how both calculations should point you to the same limiting reagent. If for some reason they don't, then go back and double check your calculations, and go back and even double check your reaction or the problem, because there's an error there somewhere, because both tests should tell you the same limiting reagent. Again, that's kind of why I like to do both of them, because then I have more confidence moving forward that I have identified the correct limiting reagent. Okay, so now that we know what the limiting reagent is, we can do our stoichiometry. Oops. Okay, so here is my stoichiometry, my stoichiometric calculation. When you're doing limiting reactant, you want to make sure you always start your stoichiometric calculation with the moles of limiting reactant. And here is a key thing. You want to make sure you use the moles that the problem gives you. So I do have these moles floating around, and it kind of looks like maybe I should use that, but you want to make sure that you use what you actually have, not a number that came out in your test calculations. So I am going to start with my 0.5 moles of chlorine. And the nice thing about this one being simpler is I am looking for moles of sodium chloride, so I just use my mole ratio. So my moles of chlorine will cancel, and I am going to moles of sodium chloride. And that is the only calculation I need. And of course, it is a very easy one. And I should get 1 mole of sodium chloride. And you can see here that that has canceled as well. Okay, so limiting reagents, I know, tend to throw people for a loop, so let me make sure that there are no questions. And, well, we probably won't do it in this live stream, but you can use ideal gas law with limiting reactants too. And let's move on to our next limiting reactant problem. So in this case, I'm actually going to take the same reaction, but I'm going to make the numbers a little bit more difficult. So in the previous question, you could have maybe looked at it and just said, well, this is a 1-to-2 ratio. I can figure this out without having to write too much down. And you could have, because the math was pretty easy to do mentally. But it's always good practice to just write down each step so that you stay organized in your mind, and then when you get to more difficult problems, you already know how to organize your thoughts and organize your calculations. Okay, let's read our problem. If 37.2 moles of sodium react with 18.9 moles of chlorine, how many moles of sodium chloride are formed? So again, even though the ratio is 1-to-2, it's very simple. This is one that maybe you wouldn't just do in your head like we could have done the last one. So let's run through our exact same steps here. First, we are going to test. And just like before, I'm going to start with my moles of sodium, but I will end up testing both the moles of sodium and the moles of chlorine. Okay, so 37.2. Oops, that didn't turn out so great. Moles of, whoops, that's sodium, not chlorine. And I am going to convert that into moles of chlorine. Again, I want to find out if I'm going to use all of my moles of sodium, how many moles of chlorine would I need to do that? Okay, so this is 18.6 moles of chlorine. My pen is just not really working very well tonight, is it? Chlorine. Again, this is what is needed. This is a theoretical calculation just so I can help myself determine what the limiting reactant is. Okay, so if I'm going to use all of my moles of sodium, I'm going to need at least 18.6 moles of chlorine. Well, how many do I have? If I go back to the problem, you can see I have 18.9. So not a whole lot more, but I do actually have more moles of chlorine than I need. That means that chlorine is in excess. If chlorine is excess, that means sodium is my limiting reactant. So again, I'm going to circle sodium. I'm going to circle it properly in my balanced chemical equation. And you can see I've already written down excess here. So I have identified my limiting reactant, but I like to test both reagents. So I've tested sodium. I'm going to test chlorine. I should get the same answer. This test calculation should also tell me that sodium is my limiting reactant. Okay, so now I'm going to start with my 18.9 moles of chlorine. And again, the question I'm asking is, if I'm going to use all of my moles of chlorine, how many moles of sodium do I need for that? This is going to be 2 moles of sodium in the numerator. That is an M. Okay, so this gives me 37.8 moles of sodium, again, needed. And let me rewrite that. Sodium. Okay, so again, I'm going to work through my logic here. Excuse me. If I'm going to use all of my chlorine, I need at least 37.8 moles of sodium. I'm going to go back to the original problem. How many moles do I actually have? I only have 37.2. I don't have enough. I'm going to run out of my sodium. So again, this points to sodium being the limiting reactant. I have already circled it in my chemical equation. And again, I like to make sure I underline here so that I know for sure what I need to use when doing my stoichiometry. Okay, so now that we are confident that we have identified our limiting reactant or our limiting reagent, we are going to do our stoichiometric calculation. All right, so I'm going to start with my moles of my limiting reactant, which is 37.2 moles of sodium. Now I am ready to predict products, and the great thing is they just want moles of sodium chloride. So this is going to be a very easy calculation. I just use my mole ratio to convert from sodium to moles of sodium chloride. And of course I get 37.2 moles of sodium chloride. Make that a little bit bigger. Okay, so again, hopefully you've seen that I'm doing the same steps even though my numbers are different. So again, just like with the more simple stoichiometry problems, there is a method to doing these problems, and I really want you to see the overall method, and then it's very easy to change little pieces within it when approaching these problems. Before I go on, let me just make sure that there are no questions. Okay, it looks like we are good. So let's move on to another limiting reagent problem. Okay, this one reads 52.6 grams of potassium is reacted with 13.5 grams of oxygen. how many grams of potassium oxide are formed. All right, so I know it's stoichiometry because I'm given information about potassium and oxygen, and I am asked about potassium oxide. So I need a balanced chemical equation to relate these two. There it is, right there. I know it's a limiting reagent problem because I'm given information about the potassium and the oxygen, both of my reactants. So I need to first identify which one is going to run out first, which one is going to limit me before I predict products. Now, this one obviously is a little bit more difficult because we have been given grams and of course we are asked for grams, but our methodology is going to be very, very similar. So my first step is going to be converting both of these grams, the grams of potassium and the grams of oxygen, into moles. Because to do anything, whether it's to do our stoichiometry and predict products or to do our tests, we need to be in moles. So that is my first step. So let's convert both of these into moles. Okay, so we're going to convert. We've got 52.6 grams of potassium. Let's convert that with the molar mass. That is 39, so 9.0983 grams of potassium over 1 mole of potassium. That grams is a little wonky. Okay, so that means we have 1.35 moles of potassium. Let's next convert our grams of oxygen. So we have 13.5 grams of oxygen. Just convert that. This is 31.9988 grams of oxygen over 1 mole of oxygen. Or sorry, that's in the numerator. Okay, so this is going to give us 0.422, I lost my decimal, moles of oxygen. Again, that M is having some problems. Okay, so now I have both of my moles of oxygen. Let's go ahead and run our test. So again, I'm trying to determine what is my limiting reagent before I do any of my stoichiometry and predicting problems. So here are my test runs. I'm just going to start with potassium, but of course I will test both of them so you can see both of them. So let's say here are my moles of potassium. If I'm going to use up all of my potassium, how much oxygen would I need to do that? Okay, so I'm just going to use my mole ratio here. This is a 4-to-1 ratio. All right, and this is going to give me 0.338 moles of oxygen. And this is what is needed. Okay, so let's think through what our limiting is going to be. If I'm going to use all of my potassium, I need at least 0.338 moles of oxygen. How many moles do I actually have? Now, in this case, I'm not going to go back to my 13.5 grams of oxygen in the problem because I have converted that. I need my 0.338 moles of oxygen. I have 0.422. I have extra. I have excess. That means that oxygen is in excess, which means that potassium is going to be my limiting. But let's run through this calculation starting with oxygen instead so that we can see both tests are going to give us the same limiting reagent. So this time, instead of starting with my moles of potassium, I'm going to start with my moles of oxygen. And so now my 1 mole of oxygen is in the denominator. I'm converting to moles of potassium. And this is going to give me 1.69 moles of potassium. Again, this is what is needed. Okay, so let's think through our logic here. I need 1.69 moles of potassium. How much do I actually have? Well, I only have 1.35. I do not have enough. My potassium is going to limit me. It's going to run out. Again, I've already circled it in my balanced chemical equation. Potassium is my limiting reagent. Now I'm kind of running out of space here. So because I have identified my limiting reagent, I am actually going to get rid, I'm just going to delete here these tests because I want to keep my moles here. So I am just going to erase this so I have space to do my actual stoichiometry. But if you're hopefully doing this on a piece of paper, you can list all of these steps and keep on working down the page. Okay, so now here for my stoichiometry. Okay, I'm going to start with my moles of my limiting reagent. That is my moles of potassium. This is why I wanted to keep this calculation up here. Now I'll use my mole ratio to predict my products. In this case, I'm predicting potassium oxide. So my moles of potassium here go in the denominator. I am going to moles of potassium oxide. Again, these are just my stoichiometric coefficients. And because it asked me for grams, I'm going to put one more conversion factor in here. I'm going to convert from moles to grams. So I do have the molar mass of potassium oxide. And that is 94.196 grams per mole. Okay, so if I do this calculation, I'm going to get 63.6 grams of potassium oxide. And that is that problem completed. Okay, let's check and see if there are any more questions. And it looks like everybody is following me, so that is fantastic. And I think we've got time for one more problem. These limiting reagent problems do take some time. Okay, so 28.6 grams of calcium permanganate reacts with 56.2 grams of lithium nitrite. How many grams of calcium nitrite are formed? Okay, so we definitely have a stoichiometry problem because we're given information about our calcium permanganate and asked about our lithium nitrite, given information about calcium permanganate and lithium nitrate and asked about calcium nitrite. So we have our balanced chemical equation to link all three of these different compounds together. Okay, that's great. It's definitely a limiting reagent because I have information on both of my reagents and I need to figure out which one is going to run out first. So because we are in grams, our first step is going to going to be converting from grams to moles using our molar masses. So let's get started with our conversions. And I do have these molar masses. Okay, let's convert. I'm going to try to write a little bit more compact, so maybe I can get the full calculation on one page. We'll see if I make it. Okay, so 28.6 grams of calcium permanganate. Now that molar mass is 277.949 grams per mole. Okay, and that will give me 0.103 moles of calcium permanganate. Okay, great. That's one down. Let's go to our next. Now let's do our lithium nitrite. That is 56.2 grams. And that molar mass is 52.947 grams per mole. Okay, and that will give us 1.06 moles of lithium nitrite. Okay, first step is done. We've converted our grams into moles. Now it's time to do our test calculations. Okay, I'll start with my moles of calcium permanganate. If I'm going to use all of my calcium permanganate, how many moles of lithium nitrite will I need? Okay, we've got 1 mole of calcium permanganate. For every 2 moles of lithium nitrite. Okay, so this is going to give me 0.206 moles of lithium nitrite needed. So if that L really did not come through very well. If I need 0.206 moles of lithium nitrite, how much do I actually have? And of course, I actually have over 1 mole, so I have plenty. I have extra, I have excess. So our lithium nitrite is in excess, which means our calcium permanganate is our limiting reactant. So again, I'm going to circle it on our balanced chemical equation. But let's run through our other test calculation just to confirm that we have the correct limiting reactant identified. So in this calculation, I'm going to start with my 1.06 moles of lithium nitrite. All right, and converting that into calcium permanganate. Okay, so now we get 0.53 moles of calcium permanganate that are needed. Okay, so if we need 0.53, how much do we actually have? We only have 0.1. We do not have enough. It is going to run out. It is going to limit how much product we can make. So again, it means that our calcium permanganate is our limiting reactant, which we have already circled. So yes, we have confirmed that we did our test right and we've got the correct limiting reactant. Now, of course, I have run out of space again, so I will erase our tests and do our stoichiometry right here. Okay, now let's do our stoichiometry. Starting with my moles of my limiting reactant, which are of course right here. So that is 0.103 moles of calcium permanganate. I'm going to convert to what the problem asked me for, and it asked me for calcium nitrite. So here's my stoichiometric conversion. The nice thing is this is a 1-to-1. Going to take me far longer to write everything down than to actually do the calculation. To 1 mole of calcium nitrite. And because it asked me for grams, I have one more conversion factor, and that is the molar mass of calcium nitrite. And that is 132.089 grams per mole. Okay, let's make sure everything cancels. Yes, okay, that looks good. So if you put this in your calculator, you will get 13.6 grams of calcium nitrite. And we have finally answered our question. Okay, any questions about this? All right, looks like there are no questions. Hopefully this helped just practice doing not only stoichiometry with gas laws, but also getting you thinking about your limiting reagent and how to approach these problems. I hope you found this helpful. Please send me questions you have, topics you would like covered to Karin at chemhelpasap.com. And thank you so much for joining us.